Welcome to The Explainer. Today, we're literally cracking open our electronics to demystify that magic green board inside. We're going to explore what is essentially a bustling three-dimensional metropolis. Now, if you've ever looked inside a broken gadget, you've definitely seen one. The printed circuit board, or PCB. But what looks like a simple, static component is actually a total marvel of modern engineering. It's stacked with hidden pathways and structures that make everything from your smartphone to your car's navigation system actually function.
All right, first things first, we gotta shatter a massive illusion here. A printed circuit board is absolutely not just a flat piece of green fiberglass. I know, it's incredibly easy to look at a PCB and just see a two-dimensional surface holding some chips. But in reality, it's a carefully arranged, highly engineered 3D structure. Think of it like a complex sandwich made of insulating materials, conductive copper, drilled holes, and protective coatings, all working together in perfect harmony.
Here is the blueprint for today's teardown. 1. Beyond the green board. 2. The copper highway. 3. Going vertical with vias. 4. Protection and identification. And 5. When anatomy fails.
Okay, let's jump right into part 1, Beyond the Green Board, the 3D illusion. So the absolute crucial point here is that we're dealing with alternating layers. You have conductive copper and insulating dielectrics stacked directly on top of each other in the z-axis to build this multi-level structure. This specific arrangement is what engineers call the PCB stack-up. You've got your copper layers carrying your electrical signals and power, and sandwiched in between them, you have your dielectric layers. Now, these dielectrics are absolute lifesavers. They completely prevent unintended electrical contact between your copper layers, they hold everything at a highly controlled distance, and they give the whole board its physical strength.
Now, what's really fascinating is how this is actually built using two main materials, the rigid core and the glue-like prepreg. They work together during a process called lamination to permanently fuse our multi-story building together. The core is your sturdy foundation. It's a cured insulating sheet that might actually already have copper bonded to its sides. But how do you stick multiple cores together? Well, manufacturers use prepreg. This is a partially cured resin that's reinforced with glass fiber. When intense heat and pressure are applied at the factory, this prepreg softens, flows into every tiny gap, and then cures into a solid insulator. It permanently bonds the adjacent layers into one rigid unified board.
Moving on to part 2, the copper highway, pads, traces, and planes.
Think of a pad as a tiny parking lot or a docking station. It's the exact spot where a physical component, like a resistor or a complex microchip, actually makes contact with our board's surface. Pads are essential because they are the physical interface between the electronic components and the PCB itself. Whether a component has long pins that poke through holes in the board, or it's designed to just sit completely flat on the surface, the pad provides that exposed copper base. That is where we apply solder to create a highly secure, permanent electrical connection.
Now, if a trace is a narrow, carefully routed highway for signals, then a plane is a massive, layer-wide power grid providing low-resistance current to the entire city. Traces are those tiny copper paths you can often see wandering all across the board, carrying data, clocks, and measurements from one pad to another. But listen, when you need to distribute heavy power or a rock-solid ground connection across the whole board, you definitely don't use a tiny trace. You use a plane. Planes help spread out heat, they reduce electrical noise, and they give all your components a super reliable short path to power.
And hey, here is a surprising little myth buster to keep in mind. While controlled routing is always preferred, a sharp corner on your copper highway doesn't automatically mean your circuit will crash. There is this old myth in electronics that a 90-degree bend in a copper trace will instantly reflect signals or cause catastrophic failure. The truth? Modern design decisions are really based on signal frequency and manufacturing capabilities. Sure, smooth 45-degree bends or curves are generally preferred for precision layouts, but a standard right angle won't just magically break your everyday low-speed circuit.
All right, let's head to part 3, going vertical with vias, elevators of the PCB.
While pads are strictly for surface connections, vias are literally the elevators of our city. They feature a copper-plated barrel that allows a signal to plunge straight through the board to an inner layer. See, a trace usually just travels horizontally in the X and Y directions. But what happens when that trace runs out of room or needs to reach a ground plane buried deep inside the board? It hits a via. The copper plating inside the via's drilled hole forms a barrel, and that barrel safely carries that electrical signal straight down the z-axis to whichever layer it needs to go to.
And we actually have a few different types of elevators we can use, ranging from standard shafts that go from the roof all the way to the basement to hidden buried vias that only serve the middle floors. A through via is definitely the most common. It's drilled all the way through the board from top to bottom. But, space is a massive luxury in devices like smartphones, so engineers get clever. They use blind vias that start on the outside but stop halfway through, or buried vias that connect internal layers and are completely invisible from the outside. They even use micro vias, which are tiny, laser-drilled connections used in incredibly dense designs.
Let's actually follow a signal on a journey from one resistor to another on a double-sided board, stepping through exactly how pads, traces, and vias work in perfect harmony to complete a connection. First, the signal leaves the terminal of the resistor and enters the copper pad. From there, it jumps onto a trace, cruising smoothly across the top layer of the board. Then it hits a via, which plunges the signal down through the core of the board to the bottom layer. A new trace picks it up on the bottom, carrying it the rest of the way until it finally hits the pad at the second resistor. It's an incredibly, perfectly choreographed dance.
That brings us to part 4, protection and identification, the city's shield.
So the solder mask acts as a protective dome over the copper to prevent accidental solder bridges, while the silkscreen provides the essential street signs and labels so technicians can actually navigate the board. The solder mask is what gives most PCBs their iconic green color, though honestly, it can be blue, black, red, or even purple these days. It covers almost everything except the pads, preventing oxidation and stopping molten solder from flowing where it shouldn't during manufacturing. Sitting right on top of that is the silkscreen. This prints out component numbers like R1 or C3, which are absolute lifesavers when you're assembling or troubleshooting the board.
All of these elements, the pads, the traces, the vias, and the planes that are deliberately joined together form what we call a net, and this net must be kept completely isolated from neighboring networks. Think of a net as a single electrical family. The 5-volt power net, for instance, might include a connector pin, a thick trace, a couple of vias, and a massive copper plane, all sharing the exact same voltage. The ultimate goal of PCB design is to ensure every single point on a net is connected flawlessly without ever accidentally touching a different net.
Finally, Part 5, when anatomy fails, real-world consequences.
A broken trace or a failed via isn't just a textbook term. It is the exact physical reason your smartphone won't charge or your car's radio suddenly stops working. If a trace gets scratched or overheats, it breaks the highway, creating an open circuit where data just stops dead. If you drop a device, the physical force can cause a lifted pad, where the copper actually rips away from the board, completely losing the connection. A microscopic crack inside a via means a layer-to-layer disconnect. And a tiny solder bridge, where solder accidentally joins two separate networks, creates a copper short circuit that can completely fry a device.
Now that you understand the hidden 3D anatomy inside every device, I leave you with this question to ponder the next time your electronics take a tumble. When we look at our gadgets, we usually just see screens and plastic cases. But underneath, there's a fragile, perfectly balanced metropolis of copper planes, insulating cores, via elevators, and protective masks. The next time a device fails on you, don't just write it off as a mysterious software glitch. Think about the physical anatomy. What part of the city just broke? Did you snap a trace, lift a pad, or crack a via? Thanks for joining me on this explainer, and always keep questioning how the world around you is built.